This is part 2 of acids and bases practice problems. In this video, we're going to be looking at some acid-base reactions and predicting products and then determining which side will equilibrium favor within the reaction. So for this first question, we want to identify what the acids and bases are, and then draw arrows to illustrate the formation of the products, and then determine which side equilibrium will favor based off the pKa values. So if for this first one, we can identify our acidic proton right here, circled in blue. And then we can also see that we have a basic site on this nitrogen right here, where we have a lone pair of electrons. And then we can also see that this hydrogen that was initially on the oxygen is now bonded to the nitrogen. And so to show that new bond formation, we want to draw an arrow from the nitrogen to the hydrogen to show the formation of that new bond. And then we also have that oxygen-hydrogen bond breaking, so we would draw an arrow from the bond between the oxygen and the hydrogen to the oxygen. And so now we want to determine which side equilibrium will favor. So for this, we want to compare our two acids on both sides. So on the reaction side, we have that our acid, or starting acid is right here, which means that the nitrogen-containing compound is our base. And then we can draw in the or label our conjugate base and conjugate acid. And so what we want to compare are the pKa values that correspond to the acid and the pKa value that corresponds to the conjugate acid. And so based off of our lecture video, we know that a lower pKa means a stronger acid. So here we have lower pKa. We have lower pKa for this first one right here, which means stronger acid. And so if it's a stronger acid, that means it wants to react more than the other one, which means that the equilibrium favors the other side, the weaker acid. And so if we were to redraw our arrows or our equilibrium arrows in the middle here, we want to show the longer arrow pointed to the right and the shorter arrow to the left. All right, so for this next one, same thing. We want to first identify our acid and our base. So here we can see that our acid is the first one, which means that the KOH is our base. Whenever we see OH, especially OH bonded to a cation, so something like potassium or sodium, we want to think about separating these. So we have K plus and OH. We only do this if it is a something on that left side of the periodic table. So again, like potassium, sodium. If it's a carbon, we never ever separate this. So if we had something like this, we do not separate this into this and this. This is wrong. All right, so we have our base here, and so we can label our conjugate acid and the conjugate base. So the acid becomes a conjugate base, and that OH becomes that H2O. So that's our conjugate acid here. And that potassium just stayed the same. Nothing really changed with it. All right, so next we want to show the arrows that illustrate the formation of the product. And so we notice that this hydrogen that I highlighted in blue ends up bonded to the oxygen. So we're going to start our arrows from a lone pair on the oxygen, draw it to the hydrogen, and then same thing as in the previous question, we have that bond between the oxygen and the hydrogen breaking. So the bond, we draw an arrow from the bond to the oxygen to show that that lone pair ended up on the oxygen on the right. Now we want to determine which side equilibrium favors. And so similar to the previous one, we want to determine which one has the lower pKa, because a lower pKa means you are a stronger acid. And if you're a stronger acid, that means you're stronger. I kind of think of it like you're pushing it to the other side. And so the equilibrium favors other side, or the one with the lower pKa. And so similar to that previous question, we can redraw those equilibrium arrows to show a longer arrow going to the right and a shorter arrow going to the left. All right. For this next set of questions, it's going to be basically the same, except now we're not getting pKa values. And so we have to use those effects from the previous video to determine which side equilibrium will favor. And so as a reminder, those are the element effect, the inductive effect, resonance, and hybridization. All right, so to predict the products, first we want to identify our acid and base. And so here we can see we have a carboxylic acid, or this functional group, which you should be able to recognize as an acid always. And then that means this compound is our base. In here, we actually want to split up that sodium in NH2 into Na plus and NH2 minus. So again, since we have that sodium or potassium or magnesium or lithium, we want to separate that out into the plus and the minus, since those are an ionic, that's an ionic bond. So next we want to start with our negative charge on the nitrogen, draw an arrow to the hydrogen to show the formation of that new proton transfer or new formation of that bond. And then next we would take that bond to an oxygen hydrogen and draw that to the oxygen. And so our final products will look something like this, where we have a deprotonated carboxylic acid. So we just have that O minus. Our sodium stays the same, nothing changes with that. And then we formed a new nitrogen-hydrogen bond. And so now we have NH3 instead of NH2. And our hydrogen that was initially bonded to the carboxylic acid is now bonded to the nitrogen. All right. Here I just also labeled the conjugate base and the conjugate acid. And so now to determine equilibrium, we want to compare the different acids that we have. So we have on the or we don't have the pKa, so we can't directly compare the acids. And instead, what we can do is compare the bases. So we want to look at which base is going to be more stable. So on the one on the right, we can see that this group has resonance stabilization, while on the one on the left, so here on the NH2, we don't have any resonance. We also have a second effect, which is the element effect, where the negative charge is on an oxygen instead of a nitrogen, which is more favorable. And so this base is going to be more stable because of resonance and element effect. So we have two here. We have both resonance and element effects play a role. And so since it's more stable, that means it's more happy existing as it is. And so that means that equilibrium favors that side. And so if we want to redraw these arrows, we would show a longer arrow going to the right and a shorter arrow going to the left. And again, that's because the side that has the more stable conjugate or base is more happy, it's more stable. So equilibrium wants to exist in that direction. All right, let's do this next one here. So same thing as before. First, we want to label our acids and bases. This one's a little bit tricky because we don't really see immediately like which hydrogens would be the acidic ones. But we do see that we have a negative charge right here. And so things that have a negative charge tend to be bases. So we can label this as our base, which means that this would be our acid in this question. And now we have to identify the acidic proton on the acid. And so we know we have a couple different hydrogen options. We have the ones that are bonded here, the blue ones. We have these purple ones up here. I'm not drawing all of them in, but these are just some of the options. We also have this hydrogen on the alkyne right here. And due to the hybridization effect, we know that that hydrogen on the alkyne or the triple bond, the one shown in green, is going to be more acidic than either the blue or the purple ones. And so we know that that's the hydrogen that's going to form that bond with the lone pair of electrons in the base. And so to show the formation of that, we can show the arrow from the lone pair to the hydrogen. And then from here, we will go from the bond, the carbon-hydrogen bond, to the carbon that is bonded to the hydrogen. And so to draw our products, it would look something like this, where we basically just swapped out where that lone pair of electrons is between uh, the the alkane and the alkyne. And so here, one common mistake that some people make is that they accidentally draw an extra carbon right here. Keep in mind that since we don't show hydrogens in our final product, this now shows that there's those 3 hydrogens bonded to the end. And so we're all set for that. All right, next we can label our carbon conjugate base and conjugate acid. And then we also have this lithium that nothing changed with that one. All right, now to determine which side equilibrium favors, we would compare the base and the conjugate base to determine which one's more stable. And so we know that based off the hybridization effect, a negative charge is more stable on an alkyne or a triple bond, which has more S character, than on an alkane, which has sp3 hybridization. So this is sp, 50% S character. This is sp3, so only 25% S character. And then we don't really have any other effects. There's no resonance, there's no element effect, there's no inductive effect that is going to change between, or that is different between the base and the conjugate base. So this one here, the conjugate base is more stable than B, or the original base, because of hybridization. Which means that we favor the side with the conjugate base, so we favor the products, or equilibrium favors products. And so to redraw the equilibrium arrows, we would show a longer arrow going to the right and a shorter one going to the left to show the favoring of the product side of the reaction. All right, so for this next one, this one is also a little bit tricky because it's not immediately obvious where the hydrogen is that would be acidic. And so we can start off with labeling our base, which is the one with the negative charge. Generally, whenever we see a negative charge, we should be thinking that that's the base, because that means that there's a lone pair of electrons that's available to pick up a hydrogen. And we have this lone pair on this nitrogen right here, which means that this is an acid. And so now we want to identify which hydrogen is acidic here. And so we have these blue hydrogens right next to the carbon-oxygen double bond. And then we also have these hydrogens on the ends of the molecule. And the same thing exists on the other side. I'm just not drawing those in. And so, as I mentioned in the previous video, whenever we see a carbon-oxygen double bond, we should immediately look next door to the carbon adjacent to it and see if there's hydrogens there, because those hydrogens end up being very, very acidic due to the resonance stabilization that forms once they're deprotonated. And so these blue hydrogens are going to be much more acidic than the purple ones. And so those are the hydrogens that are going to be deprotonated in this reaction. And so our first arrow is going to be to draw that bond or formation of that bond between the nitrogen lone pair and the hydrogen. Next, we have to break the carbon-hydrogen bond. So we'll draw an arrow from the carbon-hydrogen bond to the next door atom, or which is that carbon right there. So next we can draw our products, which will be something like this. And due to the symmetry, you could have deprotonated the hydrogen on the right side of the carbonyl. You end up with the same product. I'm just showing the ones that are on the left here. All right, from here we can label our conjugate acids and our conjugate base. And again, that sodium doesn't change. It just stays the same on the left and the right side. And so from here, we have to determine which base is the more stable one. So we have base B on the left and then the conjugate base on the right. And so for this one, we kind of actually have a few different effects that are important to consider here. We have the resonance stabilization in conjugate base. However, we also have the element effect to consider, which is that nitrogen, based off the nitrogen effect or the element effect, the nitrogen should be more basic or less basic than carbon. However, the resonance stabilization actually wins out in this case, and it's a more important effect than the element effect. And in general, that's pretty common that if you see some sort of resonance stabilization for a base, generally that effect is much, much more important than any of the other ones that we've discussed. So as a result of that, we have that the resonance stabilization favors conjugate base. So the conjugate base is more stable. Because the conjugate base is more stable, that means we favor the products. So we favor the side that has the more stable base. All right, next we want to draw out the arrow. So again, we're going to have a longer arrow going to the right, smaller arrow going to the left. Right, let's do this next one. So here we have, we kind of have a more clear base and acid. The one with the negative charge is going to be the base. The one with the hydrogen, the acidic hydrogen, is going to be the acid. And here, again, we're going to start our arrow from the negative charge or the lone pair of electrons and draw the arrow to the hydrogen. Then we're going to break the bond between the oxygen and the hydrogen and draw an arrow to the oxygen. And so our products will end up having, basically we're just swapping which oxygen has the hydrogen bonded to it. And our sodium remains untouched, just the counter in here. All right, and so to compare the strength, again, we're comparing the base and the conjugate base. And so here we can see that the negative charge is on the same element. Both are oxygens, so we don't really care about the element effect. We don't really have any electron withdrawing groups, or that like the fluorines or the chlorines or the bromines, so we can ignore the inductive effect in this case. Hybridization also isn't really a huge factor, but the main difference between these two is the resonance effect, because we know that this entire group on the left can engage in resonance with that negative charge. And so the base is going to be more stable because of resonance. And so we favor the side, or equilibrium favors the side with the more stable base. So that means that the reactants are favored in this one, in the equilibrium. And so we're going to redraw our equilibrium arrows to show a longer arrow going to the left and a shorter arrow going to the right. All right, this is the last one, and this one's pretty tricky. So there's a few common errors that people make with these types of problems, and this question kind of has shows us. So sodium hydride right here. Whenever we see sodium, we should be thinking about splitting it up into sodium plus, and then here we want that minus hydrogen. And we don't really see minus hydrogen a lot. We very rarely see that within organic chemistry. We're really used, especially in general chemistry, we're used to seeing H plus. However, this is one of the few exceptions where we'll actually end up having a lone pair on a hydrogen. And so in this case, this acts as the base instead of the acid because we have that negative charge on the hydrogen. And so again, whenever you see sodium hydride, you should be able to recognize that as being the base. And so that means that this is the acid. However, here we have a few different options for the hydrogens that can be deprotonated. We have the ones that are next to that carbon-oxygen double bond right here in blue. We also have this hydrogen right here on the nitrogen. And then we also have hydrogens that are kind of scattered throughout the rest of the molecule. However, there's nothing really unique about any of those. And so here, what actually ends up happening is that the hydrogens next to that carbon-oxygen double bond are actually more acidic than this hydrogen that's circled in purple. And so the hydrogen that gets deprotonated is going to be this one right here. And so we can draw that arrow to form the formation of that bond. And then we can also show the second arrow where that carbon hydrogen bond breaks. And this is primarily due to the resonance stabilization that occurs once you deprotonate that hydrogen on the alpha carbon. And so again, a very common mistake is to deprotonate that an H2 instead. And so to draw products, we will have the sodium stays the same. We end up with H2 instead of, or because we picked up that extra hydrogen. And then we can draw our product here. And then we have a negative charge on that carbon that is adjacent to the amine. All right. So that wraps up this video. We can label our conjugate acids here, and a conjugate base. Based off the effects, it's a little bit difficult to predict which side equilibrium would favor for this last one. So you would have to look up the pKa values for the different reagents, but you wouldn't be expected to know that based off of these effects here. All right, and again, if you haven't done so already, I recommend working through those part 1 practice problems. This problem set is a lot more focused on those 4 effects. So if you feel like you're not confident with the element effect, the inductive effect, resonance, and hybridization, then I suggest kind of working through this problem set to get a better grasp on that.